Hello and welcome to day 3, lesson 2. And in these lessons, we're going to be looking at meteorology, which is another term for weather and atmospheric conditions. Now, you might think that modern aircraft are pretty bulletproof, they can fly through any conditions with the strength of the construction and the technology, but that's just not true. Weather can still pose a serious hazard to modern aircraft and modern flight operations. So it's really important as an ATSEP, if you're working on any kind of meteorological sensors or reporting systems, that you're aware of the importance of the safety. So let's now go and look at meteorology and the way we provide information to controllers and pilots on the weather. So in this lesson, we're going to be looking at these different areas. The importance of MET information, slide 4, which we'll start on shortly. Also the MET impact on aircraft, MET hazards, effects on ATS operations, effects on RF propagation, weather messages, and MET sensors and displays. So state the relevance of meteorology on aircraft operations. So as we've already stated, aircraft operations remain vulnerable to extreme weather conditions. So as part of flight planning, pilots need to access advance warning of any such conditions. Landing at the destination is still an operation that in most cases requires a minimum level of visibility. It just can't be done in fog or extremely heavy mist and rain. State the relevance of meteorology on aerodrome operations. So airports will have minimum limits of visibility for operations, below which aircraft will be grounded. Strong crosswinds can also stop aircraft using a runway. Wet or icy runway conditions can also compromise braking and steering performance. So the weather conditions at the airport or the aerodrome will definitely affect the operations. Explain the measurement and prediction systems for wind. So a device called an anemometer measures wind speed and wind vanes measure direction. And these will typically be found at an airport. The new sonic types can perform both measurements without requiring moving parts, and thus their reliability is greatly increased. And you can see pictures here of the new sonic type with the 3-pronged sensor. Explain the measurement and prediction systems for wind. So wind can be measured using weather balloons or specialized Doppler radar, as well as anemometers. From current conditions and computer modeling, we can create an accurate forecast of conditions for a large area. The ATM system imports GRIB weather forecast data files every 6 hours to assist in adjusting traffic flow plans for local wind direction and speed. Explain the measurement and prediction systems for visibility. So as we've said, visibility is an important parameter for deciding whether an airport runway can be safely used. Visibility can be estimated visually, or special sensors can measure RVR, runway visual range, and provide it as a readout. Explain the measurement and prediction systems for visibility. You will often see a figure for dew point and temperature contained in weather reports, and we can see an example on this slide. When the two are close together, poor visibility can be expected. So note that in the weather report shown, the weather, WX, is fog, FG, and temperature and dew point in this case are the same, 3 degrees Celsius. Temperature is measured at the airport and can give an indication of likely poor visibility and icing conditions. Extreme heat can also reduce the performance of aircraft engines, so temperature is an important parameter for pilots to have access to. Explain the measurement and prediction systems for pressure. Atmospheric pressure in the region of the airport is measured by an accurate barometer. This provides the QNH reading, which is safety critical for calibrating the pilot's altimeter. If this setting is not correct, the pilot may be much lower than his altimeter indicates. So it's vitally important that we measure QNH and that we make it available accurately to the pilot. Explain measurement and prediction systems for humidity. Humidity is a measure of how close the air is to being saturated with water. At 100% humidity, evaporated water in the air begins to form as liquid droplets. This is the same point at which dew point temperature equals air temperature, and this is the point at which mist and fog and rain will begin to form. Explain the measurement and prediction systems for cloud base. The cloud base is an important measurement at airports. If the decision height for the approach is 200 feet, the cloud base must be above that. If the pilots hear in advance that the cloud base is below the decision height at their destination, they may choose to divert to an alternate airport, or they may choose to continue if the forecast is for improving visibility. The cloud base is measured using ceilometers, which pulse laser beams at the cloud base at either approach end of the runway. They act much like a short-range laser-based radar. And that concludes the content for this section. So now go through, revise those slides, and then complete the revision questions, slides 4 to 23. Pause the video, and then press play when you're ready to continue. So in this next section, we're going to look at how the weather conditions impact on aircraft operations. Now, as we've already discussed, even modern aircraft are affected by the weather, certainly by icing, by turbulence, by winds. So let's see exactly how the different weather parameters are used by the pilot in judging whether it's safe to perform the flight or whether he should fly a different route or actually cancel the flight until conditions improve. Explain the impact of wind on aircraft operations. So wind can cause turbulence, and this can result in anything from mild discomfort to those on board in aircraft through to conditions that pose a very real risk to aircraft safety. Strong winds also affect the traffic flows, since if flights from opposite directions are flying with or against a 50-knot wind, that will result in a 100-knot relative difference in ground speed. If the traffic flows were planned without taking this into account, they won't work smoothly and the flow management will be spoiled. Each aircraft type has a maximum crosswind limit. When this is exceeded, it's no longer safe for them to use the airport. For this reason, some airports may have multiple runways to allow operations in most wind conditions. Explain the impact of visibility on aircraft operations. So landings and takeoffs still require a minimum visibility. Even an auto-land approach using a Cat 3B ILS should have at least 50 meters of forward visibility. This slide shows the decision heights and RVRs needed for each type of approach. Cat 3B ILS are relatively rare. Most approaches need at least a 200-foot decision height. Explain the impact of temperature on aircraft operations. Icing, it's very dangerous to aircraft. It can freeze fuel lines, reduce lift, and block airspeed and altitude sensors, causing false readings. It can also freeze windscreens, leaving the pilots effectively blind. While aircraft have anti-icing systems, these can fail or accidentally be left switched off, so it's therefore preferable to avoid extreme icing conditions whenever possible. Extremely hot temperatures, on the other hand, can reduce the power rating of aircraft engines, so operations near the limit of runway length should be carried out with caution in extremely hot conditions. Explain the impact of humidity on aircraft operations. Humidity and dew point are good indications of how close a drop in visibility is. They can be used to judge the chances of a drop in visibility. Explain the impact of clouds on aircraft operations. Clouds obviously reduce visibility. Some also contain severe turbulence. Low clouds near an airport may mean the approach can't be safely completed because visibility is below the decision height. Explain the impact of precipitation on aircraft operations. So precipitation can mean rain, snow, sleet, and hail, and they can all reduce visibility. They can also make runway surface conditions dangerous by reducing the effects of brakes and increasing the possibility of skidding. Explain the impact of pressure on aircraft operations. Barometric pressure often helps determine the type of weather you can expect. Low pressure is more often associated with unsettled weather, high winds, and low visibility, whereas high pressure normally indicates settled weather. Atmospheric pressure for a location or a region of an airport must be measured accurately and transmitted clearly to pilots. This allows them to calibrate the altimeter with the QNH setting. This is a safety critical step before commencing any approach procedure. So much so that ATC require pilots to read out their QNH setting before commencing their approach to ensure that they have set it correctly. Okay, that completes the material for this section. So review the slides from 24 to 42, including the revision questions. Press pause until you're happy with that material, then press play again. In this next section, we're going to take another look at the meteorological hazards posed to aircraft, and we'll introduce a few other terms that we haven't covered yet. Explain the hazards posed to aircraft by turbulence. So turbulence can cause violent and uncomfortable movement of the aircraft. In extreme cases, it can cause a loss of control. Turbulence is common downwind of high terrain when there is a strong wind blowing. It can also be caused by updrafts due to ground heating effects. Because turbulence disturbs the standard column of air, it can make altimeters misread slightly. Explain the hazards posed to aircraft by thunderstorms. Thunderstorms are often associated with turbulence, icing, and lightning. For all those reasons, aircraft generally try to avoid flying through them if possible. Explain the hazards posed to aircraft by icing. As per the list on the slide, there are many hazards associated with icing, and again, these conditions should be avoided when possible. Explain the hazards posed to aircraft by squalls. Squalls cause sudden violent changes in conditions and winds, though they are usually short-lived. It may be advisable to delay an approach until one has passed, although this has the potential to disrupt the smooth flow of traffic that ATC may have planned. Explain the hazards posed to aircraft by wind shear. Wind shear is any sudden strong gust of wind in any direction. Wind shear is most dangerous near the ground when aircraft are on approach, as they have little height with which to make corrections to any sudden change in flight path caused by a wind shear. Modern airborne weather radar are designed to detect wind shear and generate an alarm. If this alarm sounds, it will generally result in a go-around. Explain the hazards posed to aircraft by microbursts. Cumulonimbus clouds are the most dangerous for aircraft, and their boiling appearance indicates the turbulence they may contain. Updrafts often occur up through the middle of these clouds, with resultant downdrafts further out. These are referred to as microbursts. This slide illustrates the often alternating nature of the turbulence. Autopilots with a turbulence mode often have a much slower response, allowing the aircraft to ride out the turbulence since it will probably even out. Trying to correct for every fluctuation in flight can make the problem worse and stress the airframe even more. When wind shear or microbursts are detected or suspected, it is best to do a missed approach and go around rather than risk a loss of control close to the ground with limited time to recover. Explain the hazards posed to aircraft by runway conditions. So once on the runway, the danger is not over, as the aircraft is a very large, fast vehicle that needs to be safely brought to a halt. Ice or water on the runway can cause a serious hazard to fast-moving aircraft during either landing or takeoff. And that completes the content for this section. So revise slides 43 through 62, including the revision. Pause the video until you're happy and then press play to continue. Okay, in this section, we'll be explaining the effects on ATS operations of meteorological factors. Explain how meteorological conditions can affect separation. Radar separation may be affected by a loss of preferred sensor. So rotating radar antennas exposed to high winds can sometimes be stalled. With the advent of ADS-B as the preferred sensor, this is now less likely, as ADS-B does not require rotating antennas. If the preferred sensor is lost, minimum separation may increase, as shown from 3 to 5 nautical miles. So you can see on this part of the diagram that 3 nautical miles is the allowable minimum. If you lost your preferred sensor, the minimum separation would go out to 5 nautical miles. Note that the 3 nautical mile separation is denoted by a 3-sided triangle symbol, and the 5 nautical mile separation is denoted by a 5-sided pentagon symbol. IFR, that is Instrument Flight Rules, flights, are not usually affected by meteorological conditions unless they are extreme. Thus, IFR flights can operate at altitude and basically zero visibility, separation being provided by ATC radar. VFR flights, however, need minimum visibility at all times as the pilot must separate themselves from other aircraft and terrain. VFR flights must therefore be carefully planned with regards to weather to avoid low visibility situations. Explain how meteorological conditions can require LVO. Well, control towers usually control aircraft in their control zone and on the ground visually from the tower cab. When visibility is too poor to allow that, they may operate under special rules known as low visibility operations, LVO. LVO may require a SMGCS, that is a surface movement guidance and control system with a surface movement radar. There are stricter rules enforced during LVO regarding aircraft separation and ground movements such as taxiing. Explain how meteorological conditions can cause diversions. If the cloud height is below the decision height at the destination airport, the aircraft may have to use one of its designated alternative airports. Its flight plan should list several options. However, flying to an alternative will cause delays and changes in the planned air traffic flow. Explain how meteorological conditions causes missed approaches. The diagram below shows an approach plate typical of one in the AIP. The dotted lines show the procedure for a missed approach. Conditions such as wind shear, thundercells, and sudden loss of visibility could make this necessary. Explain how met conditions affect equipment performance. As an ATSEP, your release of an operational system for maintenance may depend on certain weather conditions remaining favourable, such as clear skies and wind direction. If they change, you should anticipate a call from the tower or the SMC desk requesting the service be restored. This should always be complied with when possible, as operational needs always come before maintenance unless safety would be compromised. Well, that completes the content for this section. So go back and review slides 63 to 80, including the revision questions, pause the video, and then press play when you're ready to continue. In this next section, we're going to look at how meteorological and weather conditions can affect radar and radio performance. This is quite important because sometimes you may have an unusual performance or seemingly a fault reported to you. It could be nothing wrong with the equipment. So you have to keep an open mind as to conditions and be aware of the kind of conditions that could cause unusual performance in radio and radar. Explain the effects of weather on radio propagation. ATSEP. Okay, anomalous propagation, or ATSEP as it is called, is due to unusual atmospheric conditions. They can cause radio signals such as VHF to travel much further than their usual 200 nautical mile range. This may sound like a good thing, but controllers may report hearing radio traffic from different sectors as interference. These conditions usually don't last long, and there's really nothing that can be easily done to prevent this problem. The same conditions may refract or bend radar signals, causing an error in the reported positions. The radar monitoring systems may detect this unless it is in a direction not covered by the system monitors. However, ADS-B should be the surveillance system most relied on and will not be affected by this phenomenon. So as an ATSEP, you can always direct the controllers to select a single sensor source for the surveillance. If you suspect that the radar systems, PSR and SSR, are causing problems in the system track, they can go to ADS-B only. Explain the effects of weather on propagation attenuation. All right, rain and other atmospheric conditions can significantly reduce the signal level getting through the atmosphere, especially above VHF frequencies. In extremely heavy rain, radar, microwave, and satellite links may be affected. So if you're getting reports of degraded performance in those conditions, if there was extremely heavy rain about, that could be the explanation. And again, there's nothing that you can do to the system to overcome that problem. Explain the effects of rain noise. Well, aircraft are designed to dissipate static charge as they pass through the air. But when their discharge features are worn or ineffective, static charge can build up and then suddenly discharge, and that causes electrical noise and radio interference. Rain droplets striking the aircraft increase the static buildup greatly. The interference can be bad enough to disrupt communications between the aircraft and ATC. If only one aircraft is affected, however, it can be concluded the problem lies in the aircraft, not our system. Explain the effects of weather on propagation and sunspots. All right, well, sunspots and solar flares can disrupt radio communications for short periods. There are prediction tools available online, and satellite links, for example, have known periods of outage annually when the satellites line up directly with the sun. So being aware of those situations helps you to explain why the problems have occurred. And again, there's nothing that can be easily done, but you can always pass the problem on to engineering if you seek a high level solution. All right, that covers the material for this section. So go back and review slides 81 to 89, which includes the revision questions. Pause the video until you're ready to continue and then press play again. Okay, moving on to section 6, and we're going to look at some of the meteorological messages that we do provide to pilots. Now, it's not absolutely critical that you understand or can interpret the messages themselves, but it is important that you understand the safety importance of these messages to pilots, and therefore the importance of the systems that you're maintaining to ensure access to the pilots for this information, and also that the information has to be accurate. So when we're providing sensors to generate the numbers, that those sensors also have to be accurate. Explain weather information channels, TAF, or Terminal Aerodrome Forecast. Now, TAF is a forecast as opposed to current conditions. It takes local geography into consideration. Note when you look at the message, the highly abbreviated form of the message, and this is typical of MET messages. Pilots get used to reading these reports, but they can be confusing to the uninitiated. Explain METARs. So as opposed to a TAF being a forecast, a METAR provides current conditions for the given aerodrome, and it's used by aircraft flying to that airport. Again, the format is highly abbreviated. Explain snow tams. Depending on where you live, you may never see a snow tam, but in colder locations and seasons, they are issued every day and valid for 24 hours unless conditions change. And obviously, they relate to snow conditions. Explain SIGMET. SIGMETs are significant meteorological reports. They're issued as required to warn of extreme conditions or unusual events, not necessarily covered by any other messages. Explain ATIS. ATIS stands for the Aeronautical Terminal Information System. ATIS is a terminal information service for aircraft approaching an airport from 100 nautical miles out or closer. So it's a close range only system. It is a recorded message that is automatically created and updated as conditions change. It saves the controllers having to read out the met information to each arriving aircraft. ATIS is transmitted on VHF and repeats continuously. It can also be received as a text message via ACAR's VDL data link.
Christchurch Information Juliet, issued at 20590 Zulu. Expect ILSBME approach. Runway 02, runway conditions, dry. Surface wind 010 degrees, 7 knots. Visibility 50 kilometers. More significant cloud. Temperature 15. Dew point 9er. QNH 9er 6. Conditions suitable for visual approach. Reported 2,000 foot wind. 330 degrees. 19 knots. On first contact with Christchurch ATC, notify receipt of Juliet.
When first contacting the approach controller, pilots need to confirm they are in possession of the current ATIS. And this is identified by a phonetic letter that changes every time ATIS is updated. So it cycles through Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, etc. If pilots don't have the correct ATIS, they will be directed to get the current message. Explain VOLMET. VOLMET transmits on HF and is received over much longer ranges than ATIS. It transmits only once every 30 minutes and provides information for several regional airports. It transmits on multiple frequencies simultaneously because only one frequency may be usable to a particular aircraft, depending on the time of day and the distance the aircraft is from the transmitting station. Note that when in range of ATIS, the VHF signal is usually very clear, whereas the VOLMET signal is often very noisy. This is due to atmospheric noise. You see the time is 19:19, so Auckland VOLMET should start transmitting shortly at 19:20. And when it does, we'll go through the 3 channels and notice the difference in sound quality. Change frequency. And on this frequency, you can't hear the signal at all. Come down to 8.8 megs. Not too bad. And 6.6 megs, best signal. So that will vary from the time of day. Sometimes one frequency will be better than others. So during the day, 13.282 megahertz may be the only one we can receive, and the other two not so good. We're now heading into early evening, and the lower frequencies are better. And that concludes this section. So go back and review slides 90 to 105, including the revision questions, until you're happy with this section. Press pause on the video, and then when you're ready to continue, press play again. That brings us to the final section for this lesson, and in it we'll look at the various sensing systems for meteorological parameters and the displays they use. So explain wind, speed and direction sensors and displays. So the aerodrome wind sensors provide real-time and averaged readings for wind speed and direction. The indications in red are the current readings. Those in amber are the 2-minute averages. So the current wind direction is indicated by the large red figures, and the red square inside the compass rose indicate wind in this display is from 160 degrees magnetic. The active runway is indicated here. It's runway 12, which equates to an approach heading of 120 magnetic. We've already looked briefly at the sensors. So for wind speed and direction, we use an anemometer and or a wind vane. The older system used moving cup and moving vane type sensors, but these pictures depict the new sonic probe types without moving parts, and that means increased reliability and less maintenance. Explain RVR sensors and displays. So here's a display for an RVR system, and you'll note that RVR is sensed at 3 places on the runway. And here's a bit of a pictorial representation of the same thing. So each set of sensors is 2 masts. One is a light source and the other is a camera that measures the light intensity, which obviously drops off as visibility drops. Note that each runway is designated according to the magnetic bearing. So 05 for a magnetic heading of 52 degrees on approach, and 23 for approximately 230 degrees magnetic on approach. Here's a photograph of an RVR installation at one end of a runway. So there will be one of these at adjacent each touchdown point and one in the midpoint of the runway. One mast carries a sensor and one mast carries a light source. So it's the drop off in light intensity between the two that correlates to RVR or runway visual range. Explain pressure, temperature, and humidity displays. So the display opposite shows all three. These figures that ATC use can either come from the Meteorological Watch Office or by local backup sensors on the airfield. Explain cloud sensors and display. So ceiling height refers to the lower surface of a cloud layer. The display opposite depicts the differing ceiling heights at opposite ends of the runway. So there's quite a difference in ceiling height, 700 feet at one end and 4,500 feet at the other. They are measured by devices called ceilometers. Now, these are basically similar to a radar, I guess, but they operate with laser pulses. So they measure the return time of the laser reflection off the clouds. You'll have one at either end of the runway, and the display will need at least two channels to show the two ceiling heights. And that includes the content for this last section and indeed for this lesson. So review the slides 106 to 124, including the revision questions. When you're happy with that, take a break, and then we'll have one last lesson for day 3.